So hopefully at the by the end of class today, we'll be able to finish basically the entire major assignment. I'm really hoping we can finish all of chapter 15 today. And if not, maybe we'll just have to do a little bit of stuff tomorrow at the beginning of class. Can I get you to take out your 15.2, the Chatelier's principle notes? If you didn't get them, hopefully I put them in the bin. I have no idea if I put them in the bin. Okay, so what I want to stress right now is that Le Chatelier's principle says if there's a disruption in a chemical system to an equilibrium, the equilibrium will shift to oppose the change of the new equilibrium, okay? So basically, if I add a compound to an equilibrium, the equilibrium will shift to use it up. You added it, so it's going to try and use it up. If I took away a compound, Le Chatelier's principle says, well, you took it away, it's going to shift to make more of it, right? If I decrease something's concentration, it's going to shift to try and increase it. If I increase something's concentration, it's going to shift to try and decrease it, to try and get back to equilibrium. That's the idea behind Le Chatelier's principle. Now, we just kind of went over a little bit of information about, okay, well, if I add a compound or if I add a chemical, right, here, if I add A, I'm really only affecting the forwards reaction. Would you agree? If I add A, well, I haven't added any AB, I haven't taken away any AB, so I can't really affect the reverse reaction, right? But because I add A, if I add A, there's more A for the B's to react to. And because there's more of these now cumulative, there's more of them to react, the system will use it up to make more AB. And so Le Chatelier's principle, again, not a lot of math, but very, very conceptual. There are 3 disturbances in which a system can resist: change in concentration, change in temperature, change in pressure. And we'll talk about those. Here, we're just getting used to, we don't really want to dive into the specifics, but we're just getting used to the way a graph looks. We'll be at equilibrium for a really long time, right, until we disturb the equilibrium. And as soon as we disturb the equilibrium, typically every concentration will eventually change. Maybe it won't change immediately, right, but it will change eventually. And so this is just kind of describing to you the process that's happening when we shift in equilibrium. And this is where we got to yesterday. So now we're talking about changes in concentration. So this is the first kind of thing that we want to talk about. What would happen to the system if HCl gas is added at point A? Okay, let's think about this. Le Chatelier's principle says, if I add something, what will the equilibrium do? It'll try and use it up and get rid of it, right? So if I add some HCl, would you agree now I have more products? Now I've got more products to use up, and so the reverse reaction will increase in rate. Does that kind of make sense? So immediately, the concentration of HCl, spikes up. Because I added HCl. Does that make sense? When I look at this graph, okay, our system slowly reaches equilibrium. But by adding HCl, our concentration of HCl spikes up. Massive, huge, big time. Did I just throw this system out of equilibrium? Yeah, I have, because I changed one or more of the concentrations, right? Now, let's talk about the shift. Because I added HCl, our system is going to shift to use that HCl up. So now both HCl and CCl2F2, both of our products, these two things will react together to produce more reactants. Because my concentration of my products has kind of increased, there's more of them now, they're going to react and make more of these. So we say it shifts towards the reactants. When I say a shift towards the reactants, all that means is that we're going to use up some of this stuff to make this. So right now, what's going to happen, I know that HCl just went up, okay? But it's gone up, all right. What's going to happen now to both of these concentrations? If we take these two things, react them together, and make that, what's going to happen to both of these concentrations now? Do you agree if they're reacting together, these concentrations will decrease? Yeah. So that's what's going to happen. If you have a shift towards the reactants, that means both of these go down and both of these what? Go up. Are we okay with that? Okay. So that's what a shift towards the reactants says. And so slowly, the concentration of CCl2F2 will go down. Also, what other concentration is going to slowly decrease? The HCl. What concentrations are going to increase slowly? Probably the CCl4 will increase, and the HF will increase. Now, here's the only part where the math comes into play. Here's the only part where the math comes into play. Which of these two concentrations is going to decrease more? Is the HCl concentration going to decrease more, or is the CCl2F2 concentration going to decrease more? What do you think? For every one of these, how many of these need to react? 2. So which one's going to decrease more? The HCl, because it's going to decrease by twice the amount. Does that make sense? Because this has a coefficient of 2, this has a coefficient of 1. So for every one of these, we're going to react 2 of those. For every 1,000 of these, we're going to react 2,000 of these. It's going to be double the change. So in our graph, we get to show these changes. Immediately, HCl spikes up. Okay, good. But then because the reaction shifts to the left, we slowly get a change in both HCl and CCl2F2. So we're going to slowly get a change, and then it's going to flatten out. Our CCl2F2 is going to slowly change as well. And it should decrease by half the amount. I'm just a crappy artist, okay? I want you to be aware of that. They're both going to decrease. What's going to happen to our products, though? Or sorry, what's going to happen to CCl4 and HF? If our two products decreased, what's going to happen to these two? They're going to increase, and they're going to increase according to their coefficients. So HF is going to rise and then flatten out, and CCl4 is going to rise, but not quite as much, and flatten out. let's just kind of take a step back. Can you see how when we added the HCl, the system opposed that change? Does that make sense? Yeah. When we added the HCl, the system shifted to oppose that change. That's what Le Chatelier's principle says, okay? Now, Le Chatelier's principle doesn't work because of magic. It works because you increase the rate of the reverse reaction, right? You added this, and because you added this, the system shifted to the left. So you used that up and you made more of that. Hopefully that kind of makes sense. Okay, so that's adding a substance. If you add a substance, boom, it's going to shift to use up that substance. This is a substance being removed. Now, this is really interesting. A substance being removed. It's really hard to remove a substance from an equilibrium. I just want to kind of show you an example. So what we have here, I've got iron 3+ ions. So in my iron 3+ ions, what color are these iron 3+ ions? Would you agree they're kind of orange? Yeah, orangish yellow. Okay, all right, sure. Let's call them orange, just for the sake of argument, because we've got to pick a color, and I'm not very good at being in between colors. You don't have to go back, but I'm going to go back all the way to the very beginning. How easy, remember, in an equilibrium, all our chemicals are all jumbled up and mixed together, right? How easy would it be to just remove the ABs from here? How easy would it be for you to go in here and just remove all of the ABs from here? It would be basically impossible. Yeah. Well, unless there's some specific property that's unique to that chemical, right? Well, there are some unique properties that are unique, or that are interesting to some chemicals. For example, iron 3+. When I take iron 3+ and I add hydroxide to it, when I add hydroxide, do you know what I just made? Yeah, well, I mean, I added a base to it, right? But is the solution as see-through? Is it as transparent as it was before? So what did I just make? Precipitate, right? I just made a precipitate. Well, why does iron 3+ make a precipitate with hydroxide? Do you know? Could you have predicted that? I think you could have. I would like you to do this for me, please. Take out your data booklet and go to page 6. So when I add, I've got iron 3+, and the iron 3+ looks orange. I'm going to add a drop of sodium hydroxide. Now, it's not the sodium that I care about, because sodium is a group 1 ion, and those group 1 ions basically pretty much don't form any precipitates. So sodium, I don't really care. Sodium ions, I don't really care about, okay? But hydroxide's interesting. When I add this hydroxide to my beaker containing the iron 3 ions, what happens? I see hydroxide, and do you see iron 3+ anywhere in here? I do. Is iron 3+ a group 1 ion? Do you see iron 3+ here? No, so then it's in most. So the combination of hydroxide and iron 3+ makes a slightly soluble mixture. Well, what that means is it's a precipitate, right? It's going to make a precipitate. So what does that mean? When the hydroxide pairs up with this iron 3+, it's going to form a solid, right? And for the most part, that solid clumps together, and then it falls out of the solution. It makes a solid either at the bottom or at the top, depending on the density of the precipitate, right? So now, you've got this solid forming on the bottom. By making a precipitate, have I increased or decreased the concentration of iron 3+ in my solution? How many did I have before the precipitate? I had 3 here, right? And by making a precipitate, I'm reducing the concentration. Does that make sense? That's one way you can reduce a concentration. You can chemically react it and pull it out of the solution. And so that's exactly what we're doing here, okay? Concentrations can be reduced by adding other substances. So example number 1, causing a precipitate. Okay, so we made a precipitate. Let's take a look at this particular, let's take a look at that particular equilibrium. It's iron 3+, iron 3+ is orange, and what I have to do, if I want to make this equilibrium, I have to add SCN. What the hell's SCN? Do you know what SCN- is? Yeah, you could look at your periodic table. It's thiocyanate, right? Thiocyanate. Okay, well let's see what happens when I add SCN to this. Let's see what happens. What happened? Do you know what this is?
Fake blood.
It's fake blood. This is stage blood. This is what people use for blood on stage, right? Okay, so I just, all right, whatever, we just made stage blood, okay? So what's the color? By adding iron and thiocyanate together, I made iron 2 thiocyanate. Now, what color is iron 2 thiocyanate? Yeah, it's like a reddish brown, but we're going to call it red. Is that okay? It's a really deep red color. It's a really deep red. Now, if I add any more of this stuff, this stuff's going to increase. It's going to shift to the right, and it's going to make more red color. Okay, how could I make this solution more orange? Instead of adding this, what could I do to one of these two things? I could take it away. When I take away one of these two things, I'm decreasing the forwards rate of reaction so that I really only have reverse reaction. By decreasing any one of these two things, the equilibrium will shift to make more of it. If I decrease it, the equilibrium makes more of it. What's the only way the equilibrium can make more of it? By turning this into that. So what's going to happen to my concentration of iron thiocyanate? It's going to decrease. By me removing this, the system will compensate by turning this back into that. And so that's what's going to try to happen, okay? So now I'm going to try and do this as best I can. I'm going to make a little bit of the iron thiocyanate. And so it's pretty darn red. Sometimes it's hard to see. I'm going to add a buttload of the hydroxide. Would you agree it turned more orange than it used to be? Yes. Okay, so I've successfully turned that red into orange by decreasing the concentration of the iron ions. So what happens to the equilibrium when we add sodium hydroxide? Well, what did happen? Immediately, what was the first thing that changed? What was the first thing that happened when we added the hydroxide to the iron 3+ ions? We formed a precipitate, right? So what did that do? Did that increase? Did us forming a precipitate, did it increase or decrease one of these concentrations? It decreased. What did it decrease? Which one? It decreased the iron concentration. So immediately the concentration of Fe3 plus decreased. And it's because we made a precipitate with hydroxide. Hopefully that doesn't get complicated, W/OH minus with hydroxide. Okay, now this is the way I like to do Le Chatelier's principle problems. I like to draw arrows on my reaction. If I decrease this, which way is our reaction going to shift? Is it going to shift towards the reactants or is it going to shift towards the products? It's going to shift towards the reactants. If you decrease this, the equilibrium will try and make more of it, right? So by us decreasing this, the equilibrium shifts to the left. Now shifting to the left and shifting to the reactants is the same thing. Hopefully that makes sense. So the shift that we see is towards the reactants or the left. Now, because we shift to the left, because this equilibrium shifts to the left, what concentrations go up and what concentrations go down slowly? Because we're shifting to the left, we're taking this and turning it into this. So what happens to the concentration of iron 3 plus slowly? It increases. So slowly, the concentration of iron 3 plus increases. Do you see how these two will always be opposite of each other? Does that make sense? The immediate change and the shift from the equilibrium are opposing each other. If I decrease it, the equilibrium increases it. Now, iron 3 plus isn't the only thing that's made, right? Every time we make iron 3 plus, what do we also make? Our thiocyanate, right? Yeah. So our SCN is going to increase as well. But that's slowly, right? Not immediately, but slowly it increases. And then what happens to the concentration of iron thiocyanate? Yeah. So our concentration of iron thiocyanate decreases. Does this way of thinking, does this immediately and then the shift because of the immediately and then the slowly, does this kind of make sense? Okay, hopefully. I'm trying a new way of like organizing the information for Le Chatelier's principle. That's not the only way we can remove something, right? I can cause a precipitate and that'll remove something. Okay, sure. I could also do an acid-base neutralization. Instead of iron 3 plus, let's say I had some sort of an acid or some sort of a base or something like that. In here, can you identify anything in here that's an acid or a base? What? What is an acid or a base? Nina? Yeah, that hydroxide's a base. A big time. Okay, so if we have that hydroxide, what are we going to have to add to here in order to...
Could all grade 9 students whose last name begins with C or D and who have not previously gone to the nurse, please come down to the cosmetology classroom?
That's not a job I envy. Do you know what I mean? Going on the intercom every single day and having to say something in front of 1,900 people every single day, that's not a job I envy. So I really empathize with her. In here, what could we add drop by drop to decrease this concentration? Does it have to be HCl? any what? Any acid at all, right? And I'm going to say H plus just for simplicity, right? Any acid at all, right? So as soon as the H plus and the hydroxide combine together, right, they disappear. So we've decreased its concentration. Okay. So what happens when we add HCl to the system? Immediately, right? Immediately, what's the first thing to change? Which one of these four things is the first thing to change when we add HCl? That hydroxide. Is it going to go up or down? That hydroxide is going to go down. So I'll draw an arrow down. Now, can you immediately see which way this is going to shift? If you take this away, which way is it going to shift? Towards the products to make more of it, right? So we shift towards the products. And what's another way of saying shifting towards the products? Shift to the right, yeah. Oh. Well, if we shift towards the right, which things are going to get used up and which things are going to get made? If we shift to the right, what does that mean? Which concentrations go up and which concentrations go down slowly? What happens to our CO2 minus? Hey, that should be CO3 2 minus. That's my bad. Sorry. What happens to our concentration of carbonate if things are shifting to the right? Slowly going to decrease. Does that make sense? This stuff is turning into that stuff. So slowly, the concentration of carbonate decreases. Well, what else is going to decrease? Water. But what?
It's a liquid in a heterogeneous.
It's a liquid in a heterogeneous reaction, right? There's a 99.99999% of this stuff is all water, right? So if we take a little bit of the water away, its concentration doesn't decrease because it's all water, basically. So water we're not going to talk about. Is that okay? We're not going to talk about water because it doesn't do anything. So slowly the carbonate decreases. Slowly the hydroxide will what? Will increase. Slowly it'll increase. And then slowly the HCO3 minus will increase as well. That's Le Chatelier's principle in a nutshell for concentration changes, okay? Now we got kind of two more things we want to talk about. We want to talk about temperature changes and we want to talk about pressure changes as well. Oh yeah, okay. I guess we'll do an example. If at point A some of the CCl4 is removed from the system, what would happen? So let's work through this. What's the first thing that happens? If we decrease this, then CCl4 will spike down. Does that make sense? It's a very quick change, right? Boom, it changes really fast. Because we decrease CCl4, which direction are we going to shift? We're going to shift to the left. So what's going to go up and what's going to go down? Slowly, what's going to happen to CCl4? We decreased it, so the equilibrium will slowly increase it. Now, I want to be very clear. Are we going to get back up to the same level we were before? No, because you've taken something away, right? So you're never going to get back up to that level, but you can increase it a little bit. So it's a slow increase. It's not a spike. It's a slow increase. HF will also increase, and it'll increase at twice the size, right? Because it's got a coefficient of 2. What will happen to our CCl2F2? it'll decrease, right? Because we're shifting to the left, we're using this up and turning it into that. So this is going to decrease, and this is going to decrease as well. And then it'll establish a new equilibrium, right? And that new equilibrium will be established until we disturb it again for the rest of time. Can you see the difference between an immediate change and a slow change on a graph? An immediate change, what does it look like? Looks like a spike down or a spike up, right? Boom, immediate change, and then slowly we change. Okay, cool. Temperature can be thought of as an entity in Le Chatelier's principle. So exothermic reactions are also negative enthalpy. You don't know that. You don't know what the word enthalpy means, and that's totally fine. It's okay. Don't worry about it. What that means is if I have a reaction A plus B gives me C, I'm expressing this as the reaction is losing energy. If something loses energy, it's giving it away to its surroundings. So that's what an exothermic reaction is. They also have heat on the products side. Endothermic is the exact opposite. Endothermic or positive enthalpy reactions have heat on the reactant side. The system's going to shift to remove the extra heat if we add it, or to create more heat if we remove it, right? When you change the temperature of reaction, you change the value of Kc, right? Just please recall that. That's the only way you can change Kc, right? Is by changing the temperature. So how do I add heat to this? If I had this equilibrium, that's not that equilibrium. If I had this equilibrium, how could I add energy to it? You just heat it up, right? You just put it over a flame or put it in a hot water bath or something. How could I take energy away from this equilibrium system? Cool it down. I could put it in an ice water bath, right? Something like that. Okay, sure, no problem. Okay. Here's a reaction. It's the exact same reaction we've kind of been talking about right now. If we heat the following system, where do you see energy inside this system? Is it a reactant or is it a product? It's a reactant. We can do the exact same thing we just did, okay? If I heat this up, am I adding energy or taking it away? I'm adding energy. I'm adding it. So which direction is this going to shift? Is it going to shift to the right or the left? If we add heat, it's going to use up that heat and turn it into something else, right? So we're going to shift to the right. Now, immediately, what concentrations change? Did I change any of these concentrations by adding or taking them away? No, nothing. There are no spikes up and down in concentrations, okay? The shift here is to the right. And because I shift to the right, what slow changes are we going to see? What's going to happen to CCl4? If we're shifting to the right, does that mean we're using it up or are we making more of it? We're using it up. So CCl4 and HF will decrease, comma. CCl2F2 and HCl will increase. Does that kind of make sense? Yeah, we're treating this energy like any other term. It's just we're not graphing its concentration, so there's no immediate change. That's all. Okay, so I want you to try this out. Just you try it out. If we cool down the system, what direction will the equilibrium shift? That's all I care about. What direction will the equilibrium shift? That's all you got to tell me. If you cool this down, I'm going to give you 15 seconds to think about it. Okay. If we cool this system down, what are we doing? Are we adding energy or are we taking it away? So what kind of an arrow would I draw under the 95.5? Up or down? I draw a down arrow. So what's going to happen? Which direction is this equilibrium going to shift? If I take it away, it's going to shift to make more of it. Does that make sense? So we're going to shift to make more of it. So it will shift to the right or towards the products. Hopefully that makes sense. That's a tough one. Okay, that's tough. We got 5 minutes before we're going to do this quiz, so we're just going to keep motoring on. Okay, we're going to keep moseying. This one is like a crazy question, okay? It's really not that crazy, but it's for the first time you've ever thought about it. This is a very interesting question. So, when we increase the temperature of the following equilibrium system, does the equilibrium constant increase or does it decrease? Remember, when you change the temperature, that's the only time Kc changes, right? So by increasing the temperature, yes, the Kc will change. So what are we doing? By increasing the temperature, are we adding energy or are we taking it away? We're adding energy. So which way will we shift? Will we shift to the left or to the right? Because we add energy, it'll use it up. So we'll shift to the left. What I want you to think about is slowly which concentrations increase and which concentrations decrease.
Could the grade 9 students who have not presented to the nurse previously with the last names E, S, G, or H, please go to the cosmetology classroom.
Because we shift to the left, what's going to happen to the SO2 concentration? It's going to increase, right? Shift to the left, we're going to make more of it and use this up. So that's going to go up. We're also going to increase our O2 concentration. And what's going to happen to SO3? It's going to decrease. Oh, okay, 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 all right, okay, okay, all right. In general, what is Kc? It's the equilibrium constant. It's the number that defines whether or not things are products favored or reactants favored, right? Okay. There's a couple ways to think about this. What just happened to our products concentration? Look at the only product on here and what happened to its concentration. It went down. What happened to our reactants concentration? They both increased. In general, what is Kc equal to? Products over reactants. And if our reactants went up and our products went down, what happened to our Kc? Did our Kc value go up or go down? Down. Would you agree, when you reduce the numerator, your fraction will decrease, right? Also, when you increase the denominator, your fraction will decrease, right? So Kc, what happened? Did it increase or decrease? Kc decrease. Holy macaroni. Are we okay with that? All right. Goodness gracious. Yeah, we got a little bit to go still, but we'll talk about that tomorrow if that's okay with you.